Hello everyone. I'm Clément Vidal. I'm a researcher at the Vrije Universiteit Brussel, and I'm a philosopher as a background, and I got more and more interested in science as I progress through my intellectual journey. And today I want to tell you about possible life form at a stellar scale and clues of stellivores through metabolism, navigation, and propulsion. So the word clues is very important here. I'm not claiming that these are hard proofs or anything, but hopefully I will guide you through this stellivore hypothesis. So the outline of my talk will be in two parts. First, motivating the idea of stellivore. So the word comes from Latin star eater. And so I will also make a short comparison between bio and techno signatures because if I understand correctly, many of you are looking for biosignatures in the maybe more traditional senses. Then I will speak about the heat death of the universe and what it implies for intelligent life, and then go on to extrapolate also universal trends of development of civilizations. And then we'll explore some clues of stellivores through metabolism, navigation, and propulsion. Okay, so the advantage of looking for biosignatures is that it's a form of life that we know on Earth, whereas technosignatures could be life as we don't know it, so it's interestingly harder to look for this. The duration of a biosphere is, we know from Earth, could be at least 4 billion years or more. It's largely unknown for a technosphere, but some estimates conclude that other civilizations could be 2 billion years older than us. So this would leave a lot of time for a civilization to develop a lot of technology and do a lot of amazing things. If we see how our civilizations has been transformed in just 1 century, it's hard to imagine what could happen in 2 billion years. The traditional life forms would involve little spreading. Panspermia is difficult, or at least it's probably within a solar system, but it's very difficult across interstellar distances, whereas a technological species could be very fast to settle the galaxy, typically in a few million years. The disadvantage of biosignatures is that there are few targets of interest. We have all the exoplanets, of course, and a few planets in our own solar system. Whereas if you look for signals in the Gaia catalog, for example, we have 1.4 billion stars. So in principle, we could look for signals from any of these stars, or from kind of strange activities from any of these stars. The biosignatures are difficult to detect at large distances because you need very subtle spectrometric methods. A signal could be easily detectable at large distances. With biosignatures and technosignatures, actually, you could look for them in the solar system. So I'm just outlining this because there is this widespread, I think, idea that technosignatures would be very rare and hard to find and short-lived, and I think it's not true. And here is a detailed paper that makes the case for this, which is called The Case for Technosignatures, Why They May Be Abundant, Long-Lived, Highly Detectable, and Unambiguous. So now let's let's imagine that you are a civilization that is extremely long-lived. Then the major challenge at the end of time is to survive the heat death of the universe. And well, it's as you know from the second law of thermodynamics, it's almost impossible. I say almost because one way to escape it would be to make a new universe. In the sense that if a new Big Bang starts, if a new universe is spawned, then the second law of thermodynamics is reset, and heat death can be bypassed. And this was mentioned in the book about gravitation from Misner, Thorne and Wheeler in 1973. So in my work, I've speculated about a scenario where intelligent life would do that, would want to make a new universe. And it leads to this idea of a universal life cycle. So basically we start with a fine-tuned universe, at least to produce structures and life through cosmic evolution, through billions of years of cosmic evolution. Then this life evolves into intelligent life and realizes the heat death doom scenarios or others, and sets itself the goal to make a new universe, and realizes that the main source of energy is in stars, and so you would want to make the most of the free energy available in the universe and eat stars, and stellivores would eventually make a new universe, and you would have a kind of cycle. So this is a one-slide summary of many arguments in my book to show the plausibility of this scenario. Obviously, it's extremely speculative, and it's very hard to test. But it makes sense with a lot of the pieces of the puzzles that we have in cosmology. And today, so we are going to focus on stellivores. But I wanted to give you the big picture that it's not just that I widely imagine that civilizations would eat stars. No, that there is a greater purpose, a greater vision behind it. So another way to come to the stellivore idea is to extrapolate universal trends. And here I'm thinking about miniaturization and energy use. So the first miniaturization is the idea that as a civilization develops, it's able to manipulate smaller and smaller scales. So the prehistoric men were able to build tools at their own scales. And nowadays we have we master micro technology. We can build things at the micrometer, and we are entering also nanotechnology, being able to manipulate genes and molecules. But if you look at the constraints of physics, we are just at the very beginning of this mastery of small scales. And yes, an intelligent civilization could really master individual atoms. Well, we might argue that we are already able to play with atoms. I think we are kind of, it's not entirely true, we're kind of found a few hacks with atoms. And basically what we do with atoms are two things: power plants and bombs, which are relatively simple devices. It's not like a complex system with a lot of feedback loops, with a lot of capabilities. So I wouldn't say we are a civilization that masters really the atomic scale. But then we could go much further with picotechnology, femtotechnology, attotechnology, zeptotechnology, yoctotechnology. And even these terms are not agreed upon because nobody talks about them, of course. Wuktotechnology, voktotechnology, down to Planck technology. And this was an idea proposed by John Barrow in his book about impossibility, and he wanted to make it a counterpart to the idea that civilization would expand outwards all the time. So the other trend is simply the energy use, and so it has been proposed by Kardashev in 1964, and it's simply the idea that the exponential growth of energy that occurs on Earth will continue up to a type 2 society civilization that would harness the power of its star. And we are presently near a type 1 society that would use the whole energy output of our planet, but we're not even there yet. And the interesting thing with this diagram is that the energy consumption curve is extremely steep, and so it's really a bit like a phase transition. And Robert Freitas, for example, he argued that if we find extraterrestrial life, it would be either a primitive biosphere or a stellar civilization or a super powerful civilization, but we are very unlikely to find a civilization like our own, which is in the middle of this phase transition. And I should mention also that I don't think it's an anthropocentric bias, this idea, in the sense that that life on Earth has been always using energy gradients in its environment, and the growth of energy use has started before human civilization. So I think the exploitation of free energy gradients is a fundamental feature of life. Another way to put it is that our planet receives only 0.00000004% of the stellar radiation. So that's a lot of energy wasted or untapped, let's say. So if we combine these two ideas of manipulating objects at smaller scales and using more energy, we come to the idea that an advanced civilization would use the energy of its star, the energy trend or the Kardashev trend, and do this with a very dense object that would be very compressed. But we can go further. So this diagram actually can be interpreted as a metabolic system at a stellar scale. Indeed, we have an energy source. The accretion flow in binary systems, in a subset of non-binary systems, is irregular. So it means that it stops and starts again. And this is also, as you know, a fundamental feature of living systems. They are able to regulate their energy flow. It's easy to see. If you don't eat at all, you die. If you eat all the time, you would also probably die. I won't ask you which death you would prefer, but and also these systems eject some jets in the case of neutron stars and black holes, or they produce novas in the case of white dwarfs. So the big question is, could this accretion flow be controlled and be sustaining a very bizarre life form? So at this point, you probably think that it's totally impossible. It would be much too hot, and it would destroy any kind of life in this kind of systems. But I would like to get back to the big question: what is life? And one common denominator is metabolism. And Robert Vrije says that life requires metabolism, a systematic manipulation of matter, energy, and information. But manipulation can only be accomplished by the application of force. So if we really want to think fundamentally about the kinds of metabolism that might exist in the universe, we need to think about which kind of force could be used to do this manipulation of matter, energy, and information. And the answer, of course, is that there are four kinds of forces in the universe. Electromagnetism. So this is the case for all life that we know on Earth, but also of computers that use electromagnetic gates to process. So in this way, we are actually we are cousins of our digital machines that are becoming more and more intelligent. But in principle, we could also manipulate gates and matter with the strong nuclear force. Maybe that's what's happening in white dwarfs or neutron stars. The weak nuclear force is more difficult to propose. I'm not aware of any proposal about weak nuclear life forms, but maybe it exists. And gravitation itself, so the weakest force in the universe, might be harnessed with once you have enough mass to make significant changes, so speculatively around black holes. And another more abstract way to think about life is to see it as networks of reactions. So all life on Earth that we know are networks of biochemical reactions, but this arrow and these elements, they don't need to be necessarily chemicals and biochemical reactions. In principle, you could have the same with nuclear life forms. It's just that, as I said previously, we don't know how to master these nuclear reactions, but advanced civilizations might be able to make autocatalytic sets of nuclear reactions to build organizations, hierarchies of them, to control them, etc., etc. So one thing I did when I started to look at the stellivore hypothesis more carefully is to look at this metric that has been used to characterize in broad terms cosmic evolution, which is the energy rate density. So it's a power density metric in erg per second normalized by the mass. So it's a power normalized by the mass. And the nice thing is that there is a kind of neat progression of systems through cosmic evolution where they are able to sustain higher and higher energy flow. Yeah, so for example, just to explain the energy rate density, the Milky Way galaxy has a huge amount of energy, but it's also hugely massive. So if you normalize the total energy of all the stars in the galaxy by its mass, then the value remains low at 0.5, while the sun is more. And living systems are typically in this area. And so how do these accreting binary stars rate? While white dwarfs are here, this is a sample of 150 systems, neutron star there, and black holes there. So this is extremely high for natural systems. So this is, I would say, one big clue that this might be living. Another interesting anomaly in accreting black holes is the following, that the rate of increase of the mass accretion rate is nearly proportional to the mass in the accretion disk involved in an outburst or flare. So an outburst is when the disk around the black hole explodes and ejects matter. And this is kind of hard to wrap one's head around this, but an astrophysicist commented that so somehow at the time of the transition, the system already seems to have a knowledge of the maximum mass accretion rate that is going to be reached later on. Which, if it's true, is quite amazing because, of course, one fundamental properties of living systems is that they are able to predict their environment. So in other words, the black hole says, I know how much I want to eat. And this is a diagram of a white dwarf around a companion star. And as you see, it's this little white dwarf that pulls up its knife and forks and starts to eat the star, and then ejects matter with a burp. So I did not commission this image at all. It's in another context, but the living eating interpretation is a very natural way for science popularizer to explain the dynamics of these systems. Okay, so now let's go to the navigation part. So imagine that we would discover an exoplanet with a GPS accurate down to 100 meters. Yeah, just imagine that we could detect this. It would be amazing, right? It would be something incredible. It would probably mean that there is a technological civilization that has installed these analogs of GPS satellites. But did you know that there is a galactic GPS accurate down to 100 meters? And I'm not kidding. Well, if you're British, you would probably want to keep calm and carry on, and it's probably say that it's probably just nature. But I wrote a paper asking whether it could be an engineering at a galactic scale. So how does this work, this navigation system? Well, it works pretty much like GPS. In GPS, you need to have at least 3 or 4 range information from different GPS satellites, and then by using trilateration, you can disambiguate the position where you're at. And it works pretty much in the same way with pulsars because they all have a unique pulse profile. So here it's represented by the different length between the pulses. And you can use almost the same algorithms that we use for GPS to determine the position of a spacecraft in space, thanks to millisecond pulsars. So another comparison that is interesting is that the global positioning system is a passive system, so it works in airplane mode. You don't need to actually communicate with the GPS satellites. Same with the pulsar positioning system. This passive mode allows an unlimited number of users. It's very accurate. GPS is accurate down to about 90 meters with a 3 nanosecond uncertainty. And the interstellar medium leaves about 100 nanoseconds of uncertainty, which leads to a 30 meters theoretical accuracy. Of course, you want your GPS system to be Earth weatherproof, and so radio signals go through clouds without any problem. In the galaxy, you want to be galactic weatherproof, and most of the work in about the pulsar positioning system is using X-rays because they go through interstellar clouds more easily. And they both allow a time of arrival navigation solution that can be used to determine time, position, attitude, and velocity. And so if you're interested in the technical details, this paper is really a good overview. And also, it's not a speculative concept. It has been successfully tested at the International Space Station with a nicer mission. And they were able to determine without any knowledge of something else the position of the ISS with a 7-kilometer position accuracy, which is not the 100 meters or 30 meters that I talked about. But this is due mainly to engineering constraints and getting enough X-ray photons to determine positions. So how might we test whether it's a kind of galactic engineering? One idea is to look at the spatial distribution. Indeed, if you look at GPS, the GPS satellites have to be well distributed to be visible from anywhere on Earth. So here you see that from this point, despite the orbits of all the GPS satellites, there are always 5 to 8 satellites that are always visible, and that allows the users to be able to determine its position all the time. And a well-known thing in pulsar astrophysics is that millisecond pulsars have a different distribution from normal pulsars. So on the top here you have the distribution of normal pulsars. So they are clearly concentrated in the galactic disk, where most stars are. So this is obviously a side-on view of the galaxy. Whereas millisecond pulsars, they seem to be quite well distributed. And so the question is, could it be because intelligent civilizations did set up this timing and positioning system at the galactic scale? And if this is true, then they should be able to move stars around. Which brings me to the question of how to move a binary star, because these millisecond pulsars are actually, most of them are in binary systems, like the initial diagram that I showed you. So there is, first let's go to the question on how to move a single star. And this brings us to the idea of stellar engine. And here you have a comprehensive bibliography of models of stellar engine. So there is not a lot of literature, but the idea has been proposed. And if you've never heard about this idea, I recommend this YouTube video about how to move the sun. And Matthew Kaplan was asked to make this video. He's a physicist, and then to do the video, he actually ended up writing the whole paper about a new design on how to move a star. Okay, but these are two ideas to move a single star. How do we move a binary star? So we need to look at the dynamics. So here you have the millisecond pulsar and its companion star that is orbiting. And one simple idea would be to create thrust by evaporating the companion star. So for example, if it wants to go forward, it just waits that the companion is at the right orbital phase and then blows a very powerful wind to evaporate the companion, and then it would create thrust towards the top of the screen here. And the neat thing is that you can, if you want to brake, it's not that difficult. You just blow in front of you, or if you want to go in that direction, you would evaporate at this orbital phase. So basically, you get the idea. You have actually, with this method of evaporating at particular orbital phases, you can actually steer the system wherever you want in the orbital plane. So the only challenge that remains is about how to change the orbital plane of the binary. And one solution would be to hit just a part of the companion star asymmetrically, and therefore create a lifting force. And so this is the model that I presented recently about a binary stellar engine. Now let's go back to accreting binaries. So most of the binary star systems, they accrete matter, they ingest matter from their companion star, but there is a subset of millisecond pulsars that are called spider pulsars that actually do the opposite. Instead of accreting the companion star, they are evaporating it. And they do this with a companion star that is very light, that can be as light as 0.01 solar masses, up to 0.6 solar masses. And from a stellivore perspective, the idea is actually quite simple. If you imagine that you are a stellivore, you're eating your star during millions of years, billions of years maybe, and then you're running out of fuel. So if you want to continue living, you need to go to another star. And so instead of eating your whole star and being stuck, you would use the remaining of the star to create as propellant, to create thrust and to go towards a nearby star. So here is an example of a transitional millisecond pulsar that doesn't fit where the observation doesn't fit a symmetrical heating of the companion star, and instead there is a hotspot that is asymmetric. So that could be a case of this situation, that there is actually a change of the orbital plane. It's not easy to test because of the time scales involved and the uncertainties, but maybe it's testable to see a change in the orbital plane. Another line of evidence that I did with some colleagues is to extrapolate the proper motion of this millisecond pulsar. So in blue you have the first spider pulsar that has been detected, and its proper motion is pretty high. And then I took the Gaia stars that are compatible with its distance, and it will reach this position with the uncertainty along the cross in 420 years, which is absolutely nothing in the cosmic terms. And the interesting thing is that there is this other star that is there And so the hypothesis here is that it's going to grab this star and exchange its current star with this new star. So this is predictive. One prediction is that it will slow down to match the velocity of this star. And so here you see it in X-rays. So you see a kind of cometary tail. And this is a radio and optical composite image of the same system. And here the same Gaia star that is here, that it appears to be going towards. So of course we are not sure that it will be a close encounter, mainly because of the universal problem of estimating distances in astronomy. So it could be, of course, just two stars that are not in the same plane, but yeah, this is intriguing. This is a clue. Another clue is this pulsar that has been found to have an anomalous acceleration, and in this recent paper, the authors really ruled out all possible sources of this acceleration, and they concluded that the most likely explanation was that it was a very close flyby from this other Gaia star. And here my interpretation would be that it did a gravitational assist to gain velocity. Of course, very speculative, but that's what you would do if you're intelligent and you want to save fuel. And this is really an intriguing situation because close encounters are extremely rare, and the space is extremely sparse. And so this is in the galactic disk, it's not in a globular cluster. So close encounters are extremely rare. So to sum up, are stellivores living systems? Well, maybe. We saw that the big picture is that super civilization would want to make a new universe to continue to bypass the heat death of the universe. These binary systems, they have boundaries, they ingest matter energy from their companion star. They appear to be converting what they suck in from the companion star. I didn't talk about it, but at least in some accreting white dwarfs, what is ejected are heavier elements than what is accreted. So and the nova explosion is not enough to produce these elements, so it means that there has to be some conversion on the surface of the white dwarf. So it's not a simple mechanism where just what comes in is saturated and goes out. There seems to be some kind of processing. The matter energy storage could be the accretion disk that stores matter, like we saw with the black hole. Extruded, so that's a function of getting rid of waste. We saw in more detail the possible motor function with the spider stellar engine ID, the binary stellar engine ID. And of course, we all agree that life processes information. And in this framework of James Greer Miller, he puts forth all these information subsystems or informational functions. But at least millisecond pulsar seems to provide a very reliable timer function. And that's it for today. Thank you for your attention, and I look forward to your questions. And here are the 3 papers that this talk was from.
Thank you so much, Clément. That was excellent. We are going to go into some questions now. So if anybody has a question, what I'd ask you to do is either write it into the chat, or if you prefer, you can ask them yourself. I would just ask that you keep your cameras off because the seminar gets uploaded to YouTube. So yeah, has anybody got any questions?
Thank you for the talk, Clément. It's very at least interesting to think about this. For a biologist, like me, is really strange to think about a concept of life in such a way. But it's interesting. My question is, okay, that I guess that this hypothesis, what is proposing somehow, is just to consider the energy and the matter in the universe as a kind of that, as if it follows general rules of the chemistry or the biochemistry on Earth somehow, at a different level, at a different scales. But in that, okay, there are several analogies and similarities that you have shown here. But for example, there are some that is very difficult to follow. Like, for example, the relationship between different binary stars, for example, or the evolution of these concepts seems to be a little bit far from we consider as life. Can you introduce these concepts in this in your hypothesis?
Yes. Yes, of course. Yes, you're kind of asking to maybe connect the dots with what we know of life on Earth to this kind of weird forms of life. Well, there are several possibilities. Oh, wait, hold on. Actually, I have a slide about this to answer. Oh, did I just answer? Yes. I will just share a slide. Bear with me. Yes. So, what I'm leaning towards is what I would call the developmental path. So it's the idea that life goes through several transformations that we've never seen before towards denser and more energy-intensive substrates. And the analogy that I generally give is that is the one of the evolution of computer hardware. So, for example, nobody would insist that today computers must be made with vacuum tubes, as the first computers were made of. So the hardware of computers has undergone many fundamental revolutions and will also have many other revolutions to come with chemical computers, with quantum computers. That's almost certain. And so the idea is that the important part is that the computer can do the fundamental Turing machine operations, so that it can do all kinds of operations, that it is so that it's Turing complete. And the way I imagine it is that life doesn't need to be tied to a substrate. What matters is that it fulfills these fundamental functions, the 20 functions that I showed at the end. And so that's why I very much like living systems theory by Miller. It just says that living systems, they do all these things, and since it's systems theory, it's you're not making any assumption about the hardware implementation. So, and then So that's a general point. But then how a planetary civilization like our own could become that, yes, that would be different. There would be many steps indeed. So one step would be to move the planet near the star and start to accrete, to get much more energy from the star, and to eventually accrete matter directly from the star. And at this point, the life form would have to be very different. But already it's an interesting path, because it makes the prediction that we should observe some planets that accrete mass from their star at a very low rate. And then there is also the possibility that it's a totally independent path of life, that our life would have taken the path of chemical reactions, and this kind of life forms would be just self-organizing with nuclear or subnuclear reactions, and it's just like a totally different kind of life, which is, yes, harder to wrap our heads around, maybe even. And then there is a power or communication station idea, that the idea that these binary systems are the most powerful energy systems in the universe, and so an intelligent civilization would come near them and just tweak them, modulate them. And here are a few references that have proposed this, that intelligent life would be attracted to these naturally occurring binary systems and just modifying them. Yeah, I hope I replied a little bit to your question.
Okay, thanks.
Thank you so much. Have we got any other questions? Just pop your hand up or write into the chat, please. Okay, in that case, we will finish up there. Thank you so much again, Clément. That was excellent. And we will see everybody at our next seminar in 2 weeks.